Subtopic 2.4, we're looking at momentum and impulse. These two quantities are not quite as straightforward as some other quantities that we've dealt with motion, but they're very useful in a few different scenarios. So first of all, we'll look at momentum, and then once we've got a good understanding of momentum, that will logically lead into discussing impulse as well. Now momentum, it's a bit of an unusual one in that it's the definition is a little bit strange, I think, in terms of physics quantities. So momentum is simply the quantity of an object that's given by the product of the object's velocity and mass. So usually we talk about a rate of change or a measurement, or in this case it's simply the product of mass and velocity. So the equation then is pretty straightforward. So the symbol we use for momentum is P, and it's simply then the product of mass and velocity. So that particular equation is an important one to be familiar with. So literally the definition of momentum is just the equation that you use to calculate momentum. So it's not as easy a quantity to relate to, because it's simply just that product. A couple of points to note about that quantity of momentum. Because velocity is a vector quantity and we're just multiplying it by the scalar of mass, that means that momentum is a vector quantity as well. So it's important to note here that direction is important. It's also important to note that we wouldn't talk about momentum as being mass times speed, so it's always mass times velocity. The units of momentum we get by simply multiplying the units of mass and velocity. So the units of mass are kilograms and the units of velocity are meters per second. So the units of momentum are kilogram meters per second. So again, it's a bit of an unusual one. If you said that something had momentum of 5 kilogram meters per second, it's not an easy quantity to draw to mind as to what that actually relates to or what that actually is. To give you a bit of an example though, imagine we have a truck that's relatively heavy and has a mass of 2,400 kilograms. And that truck is moving along with a velocity of 5 meters per second to the right. We could then calculate the momentum, very straightforward calculation here, mass times velocity. So the mass being 2,400 and the velocity being 5 meters per second to the right would give us a momentum of 1.2 by 10 to the 4 kilogram meters per second. So you can see it's a fairly easy quantity to calculate. Now I'll just mention here as well, let's say we had a car that was half as big, so a car that was only 1,200 kilograms moving at the same speed, same velocity, sorry, then obviously then the momentum will be half as great. If this truck was moving twice as fast, at say 10 meters per second, then the momentum would be twice as great. So momentum here is just it's in and of itself, it's not a particularly useful quantity. Yes, we can compare it to different scenarios where the mass might be greater or the speed might be smaller, whatever that might be. It's in and of itself, it's not really just momentum that we need to look at. There are other quantities that we need to consider. So if we then consider those different changes, have a look at a few of those effects. So it follows logically then that the momentum of an object it's going to change if we get a change in its mass. So as we said, if the momentum, if the mass is twice as big, then the momentum will be twice as great. Or if its velocity changes. So it's a fairly obvious statement, but one that we need to look at in order to make a few links to other things as well. So if we look at that second point of its velocity changing, if velocity changes, then what we're really dealing with is an acceleration. So if we have acceleration, we're basically then saying that for an object to accelerate, or for the velocity of an object to change, we know from our understanding of Newton's laws of motion, an unbalanced force must be acting on the object. So you can see there that there's a link to Newton's second law. We'll develop that a bit further in coming videos, but just wanted to draw your attention to it now as something to think about, something to keep in mind as we consider these ideas associated with momentum. Now, the concept of momentum, like I said, in and of itself, it's not particularly helpful. So it's more about looking at how momentum is involved in a few different scenarios. And the main one that we're going to look at is so the concept of momentum there. It's the underlying principle involved with collisions. So what do I mean by that? Basically, any time we have a collision, so any two objects interacting, exerting forces on each other, we have a principle of conservation of momentum. Now, we've seen a few different scenarios where we have a law of conservation. This is now a law of conservation of momentum, and what that means is that if we write it another way, the total momentum of a system, or so if we're in talking about a system, let's say we're dealing with two masses that are colliding, the total momentum of the system before a collision is the same as after, or is equal to the total momentum after. So to put that into context, let's imagine that we have two masses. We'll just call them M1, and this one's moving with the velocity U1, and another mass M2 moving towards that object, the other object, with a velocity of U2. So this is the before situation, and then after, the two objects have collided with each other and then they've bounced backwards. Now, this is a very specific case, so it's not always going to be that they'll necessarily bounce backwards. We'll need to look at what happens in terms of the size of the masses. So we'll go through a few of these examples in class, but we have those two scenarios. So for momentum to be conserved, we need to consider the total momentum beforehand, so we can call that the initial momentum, so Pi. That's going to be equal to the final momentum, Pf. But if we consider that initial momentum, we now have two objects that we need to consider. So we really need to look at the initial momentum of object 1, so Pi1, and the initial momentum of object 2, Pi2, keeping in mind that the directions of these momentums are important, but we're still adding them together. So we might say that the positive direction is to the right, so the momentum of the second one would actually be to the left, and so the value of pi2 would be a negative, but we still need to add those two quantities together. It's the total, or the sum, or the total of the momentums. Similarly, we can then look at the final momentum of object 1 and add that to the final momentum of object 2. And now, to calculate the initial momentum of object 1, that's simply m1u1, and the initial momentum of object 2 is m2u2. Following along from that, we then have the final momentum m1v1 and m2v2. So there's the full explanation, or the full equation that you could consider for two objects that are colliding. What we'll do in class is have a look at a few specific cases dealing with these scenarios. So let's imagine that the first object was stationary, so this would end up being 0. So that then means that this initial momentum would disappear, or would be equal to 0, so we'd then have m2 u2 is equal to m1v1 plus m2v2. So we could have that sort of scenario. We could have scenarios where the masses are actually the same, so m1 and m2 being equal, and having a look at what happens in those scenarios. So while this is a very general equation, there are very specific scenarios that we might deal with in order to calculate the unknown velocity of one of the objects after the collision. We'll have a look at a few of those in class and sort of dig deeper into this idea of conservation of momentum.